Have you ever stopped to think about how just one single number can grab a simple curve and then stretch it, shrink it, or even flip it completely upside down? Well, today we're diving into the pretty amazing power of vertical transformations. And trust me, it's way simpler and way more powerful than you might think.
So how does it work? How can this one little number, this coefficient we call a, act like a master control dial for an entire graph? That is the exact mystery we are going to solve right now.
Okay, so before we can start transforming anything, we need a baseline, right? A starting point. And for parabolas, that starting point is what we call the parent function. So meet our base model. F of x equals x squared. This super simple equation is what gives us that classic U shape that opens upward. Its vertex, that lowest point, is sitting right at the origin, 0, 0. This is our home base. Everything we do next is a change to this shape.
All right, now it's time to bring in the star of the show, the main character of this whole story, the coefficient a. You should really think of this number as the shapeshifter, the one that does all the cool stuff.
So what is this coefficient a? It's just the number we multiply x squared by. But honestly, thinking of it as just a number is kind of boring. Think of it more like a director. By changing this one value, we can literally command the parabola to get wider, narrower, or even completely change the direction it's facing. So how does our little director A give out its orders? Well, two ways. First, if the absolute value of A is bigger than 1, like 2 or 5 or 100, it yells vertical stretch. Imagine pulling a rubber band from the top and bottom. It gets super skinny, right? That's what happens. But if a is a fraction between 0 and 1, it calls for a vertical compression. This makes the graph look wider, almost like you're squishing it down from the top. Okay, so that covers all the positive numbers. But what about the most dramatic move of all? What happens when our a value goes negative?
Yep, the entire graph reflects over the x-axis. Just by sticking a negative sign out front, we tell that U-shape to completely flip upside down. It becomes a perfect mirror image of its former self. Pretty cool, huh? Theory is great and all, but this is the part where it really starts to click. Let's put our A controller to work and actually see these transformations happen with some real numbers. Okay, let's start with this one. G of x equals 2x squared. Just based on the rules we just went over, what's your gut telling you is going to happen here? Following the logic is everything. First step, what's A? It's 2. Second step, how does 2 compare to 1? Well, it's bigger, so we know for sure this has to be a vertical stretch. And what does that mean? It means our new graph is going to be narrower, skinnier than the parent function we started with. And if you want to see the proof, just look at the numbers. Check out this table. For every single x value, the new y value for g of x is exactly double the old y value. So our graph isn't just looking narrower, it's literally shooting upwards twice as fast. All right, so we've seen a stretch. Let's look at the flip side. What happens with g of x equals 1/2 x squared, where our a value is a fraction? So because a is 1/2, which is a number between 0 and 1, our y values are now growing slower than they used to. In fact, they're only half as big at every step. And the visual effect of that is a parabola that looks wider, or kind of squashed down. And that, my friends, is vertical compression. Okay, ready to level up? Let's see what happens when we combine these ideas, when we have two transformations happening at the exact same time. Let's check out g of x equals -3x squared. Now, don't let this scare you. The key is to just break it down. The negative sign has exactly one job: flip the whole graph upside down. That's it. And the number 3 has its own job: stretch the graph vertically by a factor of 3. So what should we expect to see? A narrow parabola that opens downward. Easy. All right, now that you've got the rules down, I want to give you a heads up on a couple of common mistakes that I see people make all the time. Knowing these little traps will help you totally master this. Okay, this is without a doubt the number one misconception. It just feels intuitive, doesn't it? A bigger a value like 10 should make a bigger, wider graph. It just sounds right. But it's actually the exact opposite. A large a value multiplies those y values by a ton, which makes the graph get super steep, super fast. It shoots up like a rocket. And a steeper graph is always a narrower graph. Please remember that. And this next one is so important. You have to pay attention to where the negative sign is. On the left, with negative x squared, the order of operations says you square x first, and then you make it negative. That's our vertical flip. But look at the right. When the negative is inside the parentheses, you have to square the entire thing. And what's a negative times a negative? A positive. So it just becomes plain old x squared. No change at all. Parentheses are everything here.
So you might be thinking, okay, this is cool, but is this just math for the sake of math? And the answer is no. These parabolic shapes are literally all around us, in engineering, in physics, and especially in architecture. I mean, think about any beautiful bridge or something incredible like the St. Louis Gateway Arch. Architects are basically just playing with the A value. If they need a tall, narrow arch, they pick a big A, a vertical stretch. If they need a low, wide arch for a different design, they pick a fractional A, a vertical compression. This math is what makes those beautiful structures possible.
So, if you take away one single thing from all this, let it be this. That coefficient, A, is the director of the parabola. It's the boss. It tells the graph exactly how to behave, how wide to be, how narrow to be, and whether it should open up to the sky or down to the ground. Look, you've just totally nailed the first and honestly the most dramatic type of transformation. But this is just the beginning. So now I gotta ask, what do you think happens when we want to start sliding the entire parabola around the screen? That's the next step, and it builds directly on everything you just learned today.